Amazing work at the intersection of biology and robotics and control. He just does such cool stuff. You'll have to see it. We have this tradition here at BARS of inviting someone who is not core robotics in the kind of traditional sense, but just does things that connects to robotics in really fundamental ways. And I think Bob is a roboticist, but also a biologist, and I think we're going to have fun. Okay.
Thank you. Thank you very much for this opportunity. It's really a privilege to talk to this group. And what I wanted to do this afternoon is to talk about grand challenges of robotics. Now, I'll give my opinion, but what I really want is your opinion of this extraordinary group of roboticists. It's an incredible opportunity to know what you think about this, because it turns out that I'm on the Science Advisory Board of the new journal, Science Robotics, and they're having their one-year anniversary very shortly, and they've decided to think about grand challenges. And already this group has had a major impact in the first year of the journal, like the cover of the first issue, incredible capabilities, people flying in space, definite influence. And so as a result, I would like you, and if you would pass out some cards, to tell me what the grand challenges should be, because in a week, there's a meeting, and so far, Berkeley, Stanford, and the Bay Area, its views have not been represented. So I would love to have your opinion of what the grand challenges are. Now you say, well, what do you mean by grand challenges? Everybody asks that. So I've surveyed Europe recently, and they asked, well, should it be a moonshot, or a major barrier, or a key enabler, or some tool? And I would say yes. All of those are fine, but we'd love to have your opinion. And then I'll try to end early, and maybe we'll go around with a microphone, and you can share some of your grand challenges with the rest of the group. So I think that robotics, as we see already this morning, is really a synthetic science that leading to wonderful unifying principles that's bringing together very diverse areas that result in, I think, new connections and new collaborations, where there's a real spectrum of advances breaking all kinds of different barriers. Here are some of mine that I find interesting. You could list yours. So there's incredible cutting edge challenges ahead of us. And what I'll do is I'll share a few of mine grand challenges, and then I will ask for your selections at the end. So we are passing out cards. There's a little bin in the back door that says Grand Challenges of Science Robotics. If you would drop them in, your ideas, when you leave, that would be wonderful. I'll remind you at the end. So, of course, my opinion on these is shaped by the fact that I'm a biologist, so I think about robots that look like this. And in general, biomimetics is becoming one of the leading paradigms for the development of new technologies that potentially will lead to significant scientific, societal, and economic impact in the near future. If we look at the evidence of the number of journal papers and conference papers over the years, the doubling rate is every 2 to 3 years, which for the rest of science is 13 years. So bio-inspired design is just incredibly exploding at this time. And I think that as human technologies take on more of the characteristics of nature, nature becomes a much more useful teacher. There really is a convergence of what organisms can do with robots can do with respect to key enablers, theory, systems, and technology pulls or applications. So let me do the first one. One grand challenge, I think, is to have embodied control in materials. If you compare biological materials to engineering materials, they're still pretty different. Biological materials have light elements, where engineering has very diverse and often heavy elements. Biological materials grow by biological control of self-assembly, resulting in sufficient approximate designs, where engineers fabricate from melts, powders, and solutions towards some kind of optimal design. Biology has hierarchical structuring at all size levels, where engineering you sort of form parts with materials and there's an assembly associated with it. Biology adapts form and structure to function, where in engineering you sort of select the material according to function. And then one of the biggest differences in biology, the systems remodel to adapt to the environment. They can even heal or self-repair, where we try to build in engineering a secure design with safety margins that consider maximum loads and fatigue. If you look at what the then fundamental properties are in terms of the difference, you can summarize them this way. Biological materials are heterogeneous, that is, their natural constructions are characterized by different geometries with local adaptation of physical and chemical properties. They're often anisotropic, that is, the natural constructions have different properties in different directions. They're clearly hierarchical from nano to macro scale. And they're often multifunctional. That is, the natural constructions often couple sensing, actuation, computation, and communication. If we look at the structural design elements, nature has produced fibrous, helical, gradient, layered, tubular, cellular, sutured, and overlapping structures that allow very effective support for bodies and joints, impact protection, mobility, and weight reduction. By increasing the mechanical properties of strength, stiffness, flexibility, fracture toughness, wear resistance, and energy absorption. What's really exciting is now, in terms of all of these structural elements in biology, you see the mechanical equivalent, because there's now a range of techniques used to fabricate the architectures at the micro, meso, and macro scale. Here are some of those different techniques. So it becomes possible to embody the control. Just to give you some examples of the hierarchical structures, we've studied these organisms. These are the feet of geckos, even though they look sort of like alien feet. And if you take a look at the hierarchical structures, it's really extraordinary. Let's zoom in on a gecko's foot, and you see that it has these leaf-like structures that look like lamellae. If you zoom in on them, it looks like rugs. They have millions of hairs, tiny hairs, and if you look at an individual hair, they have kind of the worst case of split ends possible, down to the micro and even the nanoscale, and they don't stick by glue or by suction or by Velcro. They actually stick by intermolecular forces or van der Waals forces because of this extraordinary hierarchical structure. And then if you go to our Museum of Vertebrate Zoology we have on campus, they have 850 different species of geckos that have different hairs, and we wondered what they looked like. So we looked them all, and they're all different. They grow differently. They have different lengths and widths and different patterns, and we don't know why. But it's incredible diversity that's worth exploring to understand its relationship to function. Now, as we advance in beginning to make these synthetic adhesives, as some of the pioneers, Mark Rukowski and Ron Fearing, who are part of this group, have, you can see that you can get more advanced structural details of that hierarchy to ultimately, I think, making something that even is better in nature in terms of the material capability. In addition to the hierarchy, there's just the numbers are really different in terms of materials. Take sensors and actuators. If you look at a human, you have about 200 major muscles, 20,000 total. Here's a cross-section of a nerve showing all the individual neurons. And if we compare humans versus some of the most advanced machines, we're several orders of magnitude different in numbers in comparison. And if you look at how nature does, it has a hierarchical design, but it starts from the small, right? Nature, in this case of looking at actuators or muscles, generates power and force by using many tiny, small motors, from the nanometer size, organized to the micron size, so the unit of function of a sarcomere, up to the muscle centimeter and meter size. And if you look at the numbers, these little myosin motors, there's about 10 to the fourth in a muscle fiber, about 10 to the sixth muscle fibers per muscle. So there's about 10 to the 10th of these little myosin motors in muscle. And if you look at what they can do and take a cross-section of a centimeter, they can develop about 30 newtons of force per centimeter squared. If you look at the number of filaments, each filament can generate about 600 piconewtons. And if you look at the number of cross bridges or myosin motors, each one generates only 4 piconewtons. But they add up to do the extraordinary things that we see these actuators do. And so I would argue that one grand challenge would be to make a wonderful material for a robot that has the capability of what we see in biological muscle. If you look at its capability of plotting strain versus actuation pressure per density, here's where muscle falls. You'll see they're good, but they're not remarkable in terms of power density and strain. But they have extreme scalability, over 10 to the 11th orders of magnitude of mass, from tiny little insects to whales. And they have very versatile form factor and distribution, which makes them very effective. And they have compliance with variable controlled stiffness damping and power generation. We've worked on this for years in terms of measuring the capability of insect muscle. What we see is extraordinary diversity of function, from a motor to a brake to a spring to a strut, both within an individual muscle and across different species, all in a single tissue. So that's my first grand challenge of embodied control in materials. The second is the capability of producing multifunctional parts that show exaptation and sufficiency. What's an exaptation? It's a character previously shaped by natural selection for a particular function or an adaptation that's co-opted for a new use. And I would argue, as more structure and degrees of freedom are added to our robots, we're going to have to use parts for tasks beyond their original optimization, like we see in organisms. My favorite example in biology, and I'll show you a bunch of the different aspects of this, of an exaptation are tails. So tails likely originally evolved for that, but they're also good for grabbing onto things, storing fat, or even doing wacky things like this. There's a fracture plane in some animals where they intentionally actually break off their tails. There's a central pattern generator oscillator in there. The tails keep oscillating. The predator goes for the tail, and the animal runs away. Nice use of the tail. We discovered that geckos can run up a wall at a meter a second, takes 30 steps in a second. They can attach their foot in 8 milliseconds and detach it in 16. But when they add a slippery patch, what they do is have a reflex so that their tail pushes into the wall and they stop from falling backwards. So another different use for a tail. We also discovered that if they're on the underside of a leaf and they fall, they do this. So they have a zero angular momentum righting response by, not like cats twisting their body, but just by swinging their tail around. And you can make a robot do this too, which is not too hard. And then going in the rainforests of Southeast Asia, you can see they can glide. So here's the first glide recorded of an animal. You'll see it hitting the tree there. Boom. And if you zoom in on it, you see how they land. They go about 3 meters per second, and they crash head first into the tree. And then they use their tail to pull them back. And then, of course, extraordinary engineers like Mark Kukowski has built a whole series of perching and now climbing robots that use this kind of mechanism. Yes, geckos can also run on top of water, like similar to basilisk or Jesus lizards. This will slow down 15 times so they can run at a meter a second. During a monsoon, they can get to a tree. And we've studied this in the lab. So they do the slapping forces here, but also notice, look what they do with their tail. They actually use their tail for swimming as well, like a very primitive original function. And people have started to do this with robots that run on water, using their tail for steering and roll stability. Tails can also solve another problem that's difficult for robots, that when you get flipped upside down, you're not very functional. But here's an African red-headed lizard in real time. You can't quite see what they do, but if you slow it down 20 times, you can see that they can use their tail to right themselves very effectively. And inspired by the biology, Ron Fearing's group has made an incredible robot that uses its tail to right itself. I think Carlos, the student, might even be here. I don't know if I see him. Is he here somewhere? Anyway, so beautiful, simple solution to being flipped over. We also discovered that lizards turn in a way that they fold their body to reduce their inertia with lightning fast turns. This is again slowed down 20 times. And Ron's Fearing group has produced robots that on a slippery surface can turn using their tail, which is pretty cool. We also discovered this behavior. We think it can be modulated by the tail. Here's a gecko running to the edge and then flipping upside down. Once we discovered they do this, then my student in Southeast Asia could find them all because they were on the underside of leaves. So they would do this to get away, and then they would disappear on the underside of their leaf. It's incredible, cool behavior. And that got us thinking about the tails controlling potentially things like body pitch. So here's a lizard jumping off a surface that's rough, vaulting towards a shelter. We also then tricked it by making it low friction to produce a misalignment torque that we then characterize the perturbation for comparison. And here's what we found. So here's a lizard on the rough surface with a plot of tail angle and body angle. You can't see much real time, but if you slow it down, you can see the tail and the body angle are aligned pretty well as they jump to their shelter. And here's what happens when you make it slippery. Okay, look at the difference in the tail angle. Okay, it's like, whoops, uh-oh, but you can see how well they control the body pitch. Right, so they're redirecting your angular momentum from their body into their tail to control body pitch. And it's a nice controller. So here's the normalized perturbation versus tail rotation. Even in the other direction, it works as well. And then you can make a robot do this. So here's a robot with no feedback, which then just face plants. And then here's one with feedback that stabilizes the body pitch. And then you could imagine at some point having it sort of run off a cliff and then use the tail to land on a surface and then ultimately run up that surface. We're getting closer to being able to do this with Ron and Mark's work. And then we were able to quantify this, a paper with Tom Libby, Aaron Johnston, and Evan. I think Evan might be here. Is Evan here? There he is. And did a great job at saying how effective is a tail then with respect to its possible control. So you can quantify and predict and compare different tails, not only different tails, but different appendages that can offer possible inertial control. That was a nice general characterization. Okay, so I think multifunctional parts that get co-opted and have sufficient, not necessarily optimal performance are going to be a grand challenge to move robotics forward. Likewise, to make them robust. That's one of the biggest differences, I think, between animals and robots at the moment. What is a robust system? I've asked a lot of people. No one seems to have the same definition. That's okay, but here are some of the things that make sense. And that is, it's a notion of maintained performance under specified perturbations. You're stable and complex in a new environment. You perform multiple tasks without a change in structure. You have hierarchical and hierarchical organizational architectures, acceptations, which I already talked about, and somehow you have a form of damage resistance, fault tolerant, fail safe, and maybe self-repairing, and the systems can learn, adapt, anticipate, and are aware, and even be creative, whatever that means. And with the sense of fault tolerance and fail-safe, we see redundancy and diverse architectures that are often modular. So you certainly see that in organism, and it's always hypothesized as a trade-off between robustness and the number of modules or elements that you see available. So to look at this, my student who's now a postdoc at Harvard with Rob Wood, Kaushik Jairam, looked at insect leg design. So here's an insect leg. Probably never looked at one close up, but they have spines, they have friction pads, they have claws, and they have sticky pads, gluey pads, all on the leg. And you see the leg is very flexible and very, very compliant, right? It's a pretty extraordinary structure. So here it is on the insect. So what he did was that what any good biologist does to understand function is you cut it off. And then you look at performance. And so he cut off each of the parts of the leg, and he also then removed a wide variety of legs and took it through a whole range of performances to develop what he calls a fault-tolerant index to look at the performance tests. And so here are just some of them. So there's the modified foot, or it's called the tarsus. So if you take it off and you run them on a force platform, you can't see any change in the ground reaction forces, which is surprising. Even more surprising, and I'll show you a video of this, you run them over rough terrain and they don't change their speed. You can take a plate and pull it really fast to the side and show that they can still resist perturbations, although depending on the surface, claws add stability. And you can have them climb, and even without their feet, they can use spines to do it as long as the surface has enough asperities in it. The smooth sticky pads are good when the surface is super smooth. But incredibly robust performance to foot degradation. If you don't believe me, here's feet, here's no feet over rough terrain. Okay, no significant change in speed, even though you would think that you'd argue that they should have a difference, but they don't. Now, maybe we shouldn't be that surprised about the modularity and robustness, because if we look in nature, what we see is that there's multiple appendage loss in invertebrates, one or two appendages. So if you go out and look for an animal in the field, as I did when I was in Panama and found crabs, I couldn't find one with 8 legs. They all had 7 legs because they've lost them at some point. And people even developed what they're calling a spare leg hypothesis. It's interesting to think about in terms of redundant modules. And so what Kaushik did is started removing legs and said, how does the performance look? And so here's slowed down 20 times, all of these. Here's an alternating tripod, so 2 legs on one side, the middle leg on the other. That's their normal gait. And then he removed the 2 middle legs. You say, well, they shouldn't be able to move still. They do. They hardly slow down at all, although they have roll instability, you can see, right? Then he said, well, what if I remove a tripod of legs? We always hypothesized by the ground reaction forces that these animals were bouncing along like other animals. And sure enough, they hop, they bounce when you remove 3, and they don't slow down very much at all. And then it goes to the absurd and removes 4 legs, and what you find is, they slow down a little bit, but they can still move at relatively fast speeds, which is incredible with respect to their overall robust system. So if you look at the intact versus the reduced leg number, they do remarkably well. And then Kaushik asked, using Ron's robots and a commercial robot, how well does this design do if you start removing the legs of these? He has good evidence that the body and leg design really computes sufficient control strategy using what we rely on, what we call distributed mechanical feedback. And so that design of a 6-legged creature is actually pretty good with respect to overall robustness. And what's pretty extraordinary is that crab spiders, lizards, and salamanders have specialized muscles and skeletal structures that intentionally pinch off their legs when they get grabbed by a predator or they get damaged, tails as well, that allow them to escape. This is called autotomizing appendages. The good news is they can just grow them back in a few molts. That would be nice to have in a robot, wouldn't it? Self-repair. Okay, the exoskeletons are remarkably robust. So we took a cockroach and ran it. It's about this big, this animal, this American cockroach, the one you think you don't have in your house. And they could go 1.5 meters per second, which is pretty darn fast. We look at its transition running along a track and then up a vertical wall. And here's what you see if you do it in real time. It looks like they have a rapid, smooth, vertical transition. There you see it, but if you slow it down, you see what they're really doing. They have an intentional head-on collision. We've shown this by varying everything, and they don't change their transition time hardly at all. So we've heard a lot about avoidance and trying to get around collisions. They do it on purpose because they can with their skeleton. So here's the kind of collisions that they have. And of course, Ron's group was able to take their Dash robot and do a mechanically mediated transition as well. No sensing, no anything, just using that approach. And then we wondered, well, there must be size limitations to this. And so we looked at the specific energy based on maximum speed of sort of running headfirst into a wall versus size from the smallest to the largest animals, and looked at invertebrates, vertebrates, and even some machines, and then compared it with the amount of maximum energy absorption in skin, bone, and cuticle, looked where these crossed, and found that mechanical mediated transitions are sort of most robust at about 1 kilogram or less, which just sort of fits what we see in animals and even so far in some of the robots that have been built. So there is a scaling effect in addition to the skeleton. And now there's lots of robots do this. There's a jumping robot from Mirko Kovar here at College London. It has an exoskeletal cage around it for jumping. There's planes with exoskeletal cages, and you've probably seen versions of the gimbal from the company Flyability that is in use at present, where it has this wonderful cage and is very, very safe delivery robot. And if you look how the skeleton is doing this, here's a dissection of a cockroach abdomen. You can see they have these stiff plates, but they're connected by these very compliant membranes. So they can stretch and deform relatively easily. We wondered, with respect to that deformation, maybe that's how they can seem to go anywhere, and they're found anywhere. So Kaushik looked at them going through their smallest crevices. He discovered that this animal can go through a crevice the height of 2 stacked pennies. Here's their normal standing height. Here's the tiny little gap. This is the real time. They can get through it relatively easily. They don't really have hard parts. That's the thing, right? So it's pretty extraordinary. That's extraordinary, but this is more extraordinary. And so this is the little gap it can get into. And we asked, well, what happens when it gets into that confined space? Of course, it's squished in half. I told the students, well, don't do this. This is a waste of time because they're squished in half. They said, we already did it. And here's what we found. This is the unconfined animal, real time, then slowed 20 times. Can't see it in real time because it's going 1.5 meters a second. They're slowed 20 times. That's their normal gait. Here it is confined a little bit. That's real time slowed down. You can see their gaits adjusted. But here is in the 4 millimeter, okay? I'll give you real time and then slow down. Okay, that's real time. Okay, yes, it does mean that in your ceilings, in your walls, in your floors, they're going squished in half, at least 20 centimeters a second. They are unstoppable and incredibly robust. And here's what they look like. I'm not joking. They're squished. They're squished in half. You don't see the performance drop until you really squish them in half. Now we wonder then, what are the forces like when they experience this kind of thing? And so we put them, of course, in a materials testing machine and did a stress strain analysis. They're viscoelastic. We did it at different rates. And I'll tell you that there's sympathy for a cockroach. This is great. I can tell you, no animal was harmed in this study. We ran them and flew them before and after, and there was no significant difference in their flight time or their speed. So no animal was injured in this. We didn't go to the point where we squished them. But what we did find is that they can withstand 800 times their body weight without injury, right? Incredibly robust system. So you can see he's okay. He's going to get up. He's just checking out things with his antenna. Good, he's fine. Okay. A lot of sympathy for the cockroach. And so then, using Ron's pioneering technique of smart composite microstructure, Kaushik looked at how the plates were aligned and built a robot that he called Crom, for a crawling robot with articulated microstructures. That looks like this, and here's the compressed version. It actually, like the animal did, sprawls out. It doesn't use its feet. It actually uses its spines on its leg, like the animal does. Here's a video of it. And then here's the compressed version. So it can be compressed 50%. So I think that's a grand challenge if we could build something as robust as a cockroach or an arthropod. Okay, the last one I'll share with you is the grand challenge of being able to learn and even be creative. We'll try to show an example of what that might mean. To do this, we've been studying these guys, squirrels. People at Berkeley know that there's a lot of squirrels on campus. And if you're from other universities or Stanford, you should go out and bring some peanuts and feed our study animals, because we're now starting a field we're calling cognitive biomechanics. And we're studying the free-ranging squirrels, the squirrels that are just outside, with Lucia Jacobs, an incredible professor in psychology who studies their hippocampal maps. And she said, you can just do them outside. You can mark them so you know individuals. And you can just take your apparatus outside. So this is behind our building. This is a magnetic board we created that has a beam they jump off of and a landing perch they land on. And you can do experiments outside. Here's one of the experiments. We took 3 different rods of different compliances and had the animal decide where to jump off. Okay? All right? They'll do anything for you. So there he goes. Let's slow down. Okay, so now he has a choice, right? He could either jump off the stiff end but then have a really long jump, or he could go right to the end and have an easy, tiny jump, but then he's on the very compliant part of the rod. So we hypothesized a trade-off between gap size and compliance. Do they figure this out? What do they do? I'll give you the ends of the spectrum of what they do. So here's the low compliance rod, the stiff rod. You can see they go pretty far. Here it is slowed down 10 times. So they're making the decision about where to take off. They never fall, by the way, which is, to me, extraordinary. But I guess that's true from just seeing them evade hawks in the tree. So this one goes pretty far down. And here's the other end of the spectrum, a very compliant rod. Watch the decision. Doesn't take long. Okay, boom. I'm not running down that rod. And you can see it's pretty hard for them to maneuver on these rods to grip them. So it's a challenge and an important decision for them, so that they make sure that they are able to get to the peanut, the reward. So we really have objectives and real rewards, right? So, and for a walnut, they'll absolutely do anything. It's the highest value. All right, so if you look at the data of when to leap, squirrels leap earlier on the higher compliance rods, and they go further down the ones that aren't. And it matches pretty well what you'd predict for securing a good landing. And if you look when they decide to leap and examine their landing air, it's minimized for all the rod stiffnesses. So they make very good decisions. How they do this, we don't know, but hopefully we're going to find out. And then we did another experiment in the field, looking at them on a very stiff plank for a control, and compared it to a compliant sort of diving board. Here's the animal. Here's Judy Chin, a superior graduate student in psychology. Here's the squirrel. They get up there and they take turns. We can get repeated measures on individual. Here's one trying to cut out a line. The other one says, no, go back, it's my turn. And so they actually line up like this. And you'll see people walking behind here. And they're incredibly good study animals that will behave in the natural environment, and so you train them to realize what they have to do to get the peanut, and then you can collect the data with a high-speed video. And we quantify the vertical landing error when they go off the compliant board, so it looks like this, and we trace it, and then this is the error of the center of mass trajectory, how much it is off the perch. That's the error. And then here are 5 jumps from the same individual. So there's the first one, misses pretty badly. This is really hard to jump off, by the way, if you look at how much it bends down. There's the second one, a little bit better. This is the third one. Almost there. Fourth one, center of mass, pretty close. And the fifth one, it nails it. The center of mass is right on the perch. Okay, so if you look at the data of the vertical landing error versus the trial number, the controls, they always hit it. But over time, they get better. 5 or 6 trials, they learn how to do this. Okay, and so then we thought, in terms of the representation, oh, it's just the ballistic equations. We'll see what they did in terms of horizontal or vertical position, takeoff velocity, angle, and it's not consistent with any of those. So they have a completely different representation that they're learning, and we don't know what it is, but we'll figure it out. One of the ways we tried to do this with transfer learning was to move the perch further away and up a little bit. And we wanted to see if the ones who did it before would do better than the ones that were novices. And they completely fooled us because they did this. So they parkoured off the wall, adding a control point. I don't know, this is pretty creative to me. It'd be great if we could have a robot do that without telling it to do that, right? Pretty amazing. And so let me end with some true inspiration for building a high mobility robot. When we'll be able to build a robot that does this? Pretty hard. Even harder. Okay, I like this one. So he's looking, what's going on? How do I get to the peanut? Nice. All right, this one is really hard. Like, how do you choose to land on that, right? Boom, nice. And then you have biological components that you have to deal with. Who wants to steal your nut after all that work? And then finally, you get to the peanut. Okay, the reward. All right, and so do we have robots that can do this, is the question. And they're getting there. This is a new company, Ghost Robotics, from Dan Kotichev's group, and 2 students that have created a direct drive robot that, it kind of bounds like a squirrel, but it has more energy than most. So for some leaping capabilities, I think it's moving in the right direction. They also have one now that has a bendable spine, so that's pretty energetic. And we hope that that's going to be possible in the future. And if you combine that with Ron Fearing's extraordinary robot, the students that built it are here, Salto, and its ability to jump and parkour. I'm showing the older videos because Ron's going to show the newest ones, so I'm not going to preempt that. But it's this, we start to have the elements of the right control modules and representations to begin to do this. So here it is, doing its own version of parkour off a plate. It's pretty amazing. So he'll even show more amazing videos in his talk. Okay, so come and visit Cyber, the Center for Nursery Biological Inspiration and Education and Research, where we put together biology and engineering. Also, yes, you should submit to Science Robotics, but there's another journal. If you involve biology, here's a journal that I run called Bioinspiration for Biomimetics. It has a very high impact factor. It's mostly robotics, and now the impact factor has gone over 3. Please consider sending it to our journal. And now I would love to have your selections for the grand challenges. On Tuesday, there's going to be a meeting of the board to put them into this anniversary issue, and we have no input yet. So if you don't say anything, then Carnegie Mellon and MIT are going to determine what people read are the grand challenges. Please give me your opinion on the cards, or I don't know how much time we have left, but 5 minutes? So 5 minutes. I'd love to hear you share a few of your ideas for grand challenges, but fill out the card, and there's a little tub in the back in the last door. Just drop your card into the tub, and I promise you'll be represented in the discussion of what the real challenges of robotics are. Okay, so who would like to share a grand challenge? Don't be shy. Oh, there's somebody.
Metacognition, robotic metacognition. Does the computer know if it will make a good decision or a poor decision?
I like that. We're going to write these down, so we'll get them. But you can write them on the card, too. Who else would like to share one? Oh. Yes, make sure you use the mic so we can capture it on the tape. Someone else? I know some of you. I'm going to call on you if you don't raise your hand. Come on, share your ideas. You can see your own stuff. It's okay if you do that. You're some of the best people in the world, so. Nobody wants to share? All right, Mark's willing. Who's here?
Better design tools for designing like mechanical intelligence or mechanical feedback systems.
We agree with that one. Goldberg's there. Come on. What's your grand challenge? Wait, use the microphone.
Have a robot that can pick up anything a human can pick up.
Okay. You told me a mouse was one of the potential challenges. That's really hard.
So yeah, we've been thinking about adversarial objects, so pick up something that doesn't want to be picked up, like a cockroach.
Okay. Over there?
Biocompatible sensors for surgical applications and things like that.
Yes, that's hard. That's a good idea.
I have 2. How about robots that make robots, so self-perpetuating robot populations? And how about robots that can teach each other or learn from each other?
Excellent. Excellent. Someone else had their hand up?
I was thinking something like a robot decathlon. So you have a bunch of single sports events that are fairly simple alone, and you create a single robot that's going to win the entire competition, not just any single one of these.
That's excellent. So so who knows about the Cybathon?
Yeah, I do.
Does anybody
like that.
know about the Cybathon? So this was the first Olympics last year in Zurich for disabled individuals with powered devices. I went to it. It was extraordinary. And their vision is just what you're saying. And that is in 15 to 20 years, everybody's going to compete against everybody else, including the robots in all the events. I think that would be extraordinary. Go ahead.
How about like neural interface between human and machine? Like your prosthetic arm will feel like your own arm.
Okay. Excellent. Ron has one.
Right, as our bodies get older, the robots take over more and more of our function.
That's happening. I show a cover from Science, the journal Science, where it shows all the different parts that we already swap out that we don't think about. And that's only going to happen more frequently. And what I tell my students is they're going to be the generation that ultimately determines, as parts get better than our parts, how much do you swap out? When do you cut off your leg because you can make a better one? And use that. I mean, that's gonna happen and face us, which is really interesting. Okay, thank you very much. Appreciate it.
Thank you.
Fill out the cards. Put them in the bucket.
Fantastic. Thanks so much, Bob.